Let's start. Today we are going to talk about domain adaptation problem. Let's recap the type of problems we have already seen. So far we have looked into a learning problem where we are given a training set. Let's say with M samples, so we have Xi's. I'll just call them train to make them explicit that they're in my training set. YI's, my labels, train. I have, let's say, M samples, potentially coming from a distribution. Right? So that's my training distribution. I denoted with Q, X, and Y. It's a joint distribution between my features and labels. All right, so I learn a function mapping X to Y, right? So that's the learning process. So how we learn that? We define a loss function, and then we minimize the average error on the training set. So I pick my model parameters theta by minimizing the average error that I have over my training data. F theta xi train and yi train. So this gives me theta star. So that's not the ultimate goal though, right? So we have seen in the generalization lecture that ultimately what I care is that if I take this function f theta star and apply it to my test set, I want to have a good performance. So let's say I'm given a test set, xi test, yi test. Let's say I have M prime samples from the test set. But again, the assumption is that my test samples, they are coming from the same distribution as my training samples. Let's say part of your ImageNet you're doing for training and you're keeping some of the images for your test and validation. So over this test set, we compute the test error by evaluating the function that we have computed over the test samples that had not been used during the training. Right? So the whole goal of generalization and optimization parts that we covered is to learn a function that this test error is small. So smaller, better for us. And we have seen that if we have enough samples in our training, the generalization gap, the difference between the training error and test error would be small. And also we have seen that in over-parameterized models, even though the number of parameters is larger than the number of samples is number of parameters is larger than the number of samples, again, we observe that the training and test error differences can be small. So the goal was to train a model on the training set, and if it does well, then using these results, we can make an argument that the model is going to do well in the test set as well. So that's basically the setup that we have covered in the first part of this course in terms of optimization and generalization lectures. Okay, so the question is this a realistic setup or not? So what do you guys think? So I see one answer, no. Why is that? Why isn't this a realistic setup? Okay, so I see one answer. It says the same distribution of the training set and the test set. So if you think about the assumptions here, so I'm assuming my training samples coming from distribution QXY, and also my test samples, they come from the same distribution, right? That's the key assumption that we have here. But in practice, this may not be the case. So in practice, training distribution can be different than the test distribution, right? So in general, if we want to consider a more general setup, we refer to the set that we are training on as the source domain. And the set that ultimately we'll test on, we refer to it as the target domain. And again, the distribution of samples in the test domain, let's represent them by QXY, can be different than the distributions of samples in the target domain. Let's refer to it as PXY. So these two distributions can be different from one another. Okay, so let's look at some, let me just see if there are some comments. Okay, good answers. So when we'll be in this situation that either our training or test distributions or source and target distributions, they're going to be different. Let's look at some examples. So you may have your QXY be representing some synthetic samples. These are easier to generate in many applications, and you want to train your model on these synthetic samples. But at the end of the day, you want to deploy them in real world applications when you'll have real samples. And these real samples may have some natural variations. Maybe the lightings would be different. Maybe there would be some other natural variations in the images or your samples that you had not seen in your synthetic samples. Right? Or your source domain can be samples, for example, with a particular background, let's say with a white background. So you are looking at images, the object is being highlighted, and the backgrounds have been whitened. Right? So you train your model. The background shouldn't make a difference in your let's say classification, because the main object remains in the image. But if you do that and then you apply your model in real applications, you'll need to evaluate the performance on some natural samples with various different backgrounds that it may happen. So because of these examples, and you can come up like with zillions of other examples for this is a very important problem to understand when we can train a model on a particular distribution of samples and deploy it on other samples coming from another distribution. So one point that I want to make here is that when we are saying these distributions are different, I need to highlight that they are somehow related. right? So in a hand-wavy fashion, because the distributions cannot be completely different. You cannot have, let's say, some images here in your training, and in the test you have like gene expressions, right? So these are also images, but maybe with a slight variations, some natural variations, or with some different backgrounds, so on and so forth. So we'll try to see what we mean by quote unquote being related. Otherwise, the problem doesn't make sense. Okay, so let me pause and see if there are any questions. Okay. Just as a notation, we refer to QXY and PXY as the underlying probability functions. But in practice, we observe samples from them. So when I observe M samples from these distributions, I'm going to refer to them as QXY with a script M on top of them. So this will be the empirical distribution that I'm observing from these underlying population distributions. Okay. All right, so let's see what we have in training. All right, so in training, we'll have some labeled samples from the source domain. So I have XY pairs from the source domain that I have, similar to the training set that I had in the standard learning framework that we have seen. So we have for source domain, we have labeled samples. So what I mean by that, so we are given xi, so I put a script s to highlight that they're from source distribution, xi, yi. How many samples I have? Let's say I have m sub s samples from my source distribution. So these are coming from distribution qxy, and I again label it with m sub s just to highlight that this is the empirical distribution observing from the population distribution, population source distribution Q. So sometimes I'm going to use some other notations for my source samples. I may represent them by just X, capital X sub S and capital Y sub S, the whole set of labeled samples coming from the source distribution. Just for simplicity in some of the formulations that we have. Okay, so that was about the source domain. So what about the target domain? The domain that I want, that's my ultimate goal, right? So the performance in the target domain is my ultimate goal. So I really don't care about the source domain. So for the target domain, we may end up in different situations. All right, so situation one is that we have only unlabeled samples from the target domain. And that's maybe the case in many applications because labeling is expensive. So we have unlabeled samples from the target domain during the training, but I don't have their labels. Only unlabeled samples are available. And so let's represent them by xi t, representation for the target domain. Let's say I have m sub t samples. And again, for simplicity, I'm going to show this whole set with xt, which is for the target domain. All right, so what is the distribution that these samples are coming from? Px. Right, remember Pxy is the joint distribution of my target samples and their labels. I don't have labels, so I'm just going to look at the marginal distribution on the x. So they come from distribution Px. Okay, so this problem is called unsupervised domain adaptation problem. Why unsupervised? Because I don't have any labels for my target domain during the training. So only unlabeled samples are available during the training. Okay, so that's one situation. So today we are going to mainly focus on this problem. Okay. So, but you may say, okay, labeling is expensive, but maybe I can have some few labeled target samples as well in my training. And that's a valid point. So if you have unlabeled target samples, so xt plus some few labeled target samples. Not by much that you just train a classifier on top of them reliably, but you have you may have few labeled target samples. So this problem is called semi-supervised domain adaptation. So domain adaptation, I'm going to show with DA problem. So we'll see if we have time to cover this or not, but I want to highlight that this is an interesting problem as well. All right, so the third category is the case that there is no data available about the target domain during the training. No target samples available during training. Nothing. Yes, everything here is for training. So during the training, I do not have any target samples labeled or unlabeled during the training. Then how is it possible to learn? Right, so in the domain adaptation problem, the idea was that, okay, my source and target distributions are somehow related. So if I have some unlabeled samples from the target in the source, so I can somehow learn a reliable function for the target domain as well. So that sounds reasonable. But what if I do not have any target samples in my training? So how is it even possible that my model can perform well in the test time on completely unseen domains? Tasneem, go ahead.
Yeah, I'm just not understanding how we can have labeled samples for test set during training phase also, like for semi-supervised type of thing. How can we have labeled samples in the test set?
There is no test set here. You mean the target?
Sorry, target set.
Yeah, so you can have, right? So you don't have a lot of them. Let's say you are training your classifier on samples, with like a sunny background, right? And then you want to deploy it in your whatever self-driving car or your classifier in Boston or someplace, with like a cold weather, and you have some wintry backgrounds. You can have a lot of unlabeled samples, but you may be able to annotate some few target samples. Or by collecting some data in an online fashion, you may be able to start with completely unlabeled and may gather some labeled samples. But the number of labeled samples may not be a lot in order to ignore your source labeled samples and unlabeled target samples to only use these to train a classifier, right? So that's not going to be enough for you. You may have like maybe 5 samples per class, or 5 labeled samples per class, 3 labeled samples per class. So it is not going to be enough just to train a classifier using these labeled samples. However, they can be useful in improving the performance of the model overall using these samples.
Okay, thank you.
Make sense?
Yes, thank you.
Sure. So I see a few comments. Holding out training samples as target set. So here I don't have any target. I have no idea about target samples, right? In the third case, in this case. So even if I hold out some training samples for the target, so my target can be completely different. So there are some suggestions: augment images and train the model to make it robust, bootstrap the model on training samples, learning a mapping to transform the distribution of images to standard normal. So these are good ideas, but if we step back, if your target domain is completely different than your source domain, then it may not be able to, the learning may not be even possible. So here, the idea is that you have, instead of just one source domain, you have multiple diverse source domains. So maybe you gather labeled samples not from one domain, but you have 5 or 10 different domains. And if you learn a function that does well on all of these diverse domains, it is likely to have a good generalization to an unseen domain, but still that domain should be related to at least some of your training source domains. So this problem is called domain generalization, or people refer to this sometimes as out of distribution generalization. So this will be the focus of our next lecture, depending how much we can cover today. Okay, so basically we have 3 problems. One is that you have, in all of these problems, we have labeled source samples. That's good. In domain adaptation, in unsupervised domain adaptation, I only have unlabeled target samples. In semi-supervised version, I may have few labeled ones, and in domain generalization, I have no samples from my target domain. Okay, so I see one more question. Union the domains and train using ERM. Or I don't follow. Can you unmute yourself and tell me what you mean?
No, so for domain generalization, you mentioned we train using multiple, or you have diverse source domains. So I was wondering, do we just union them and train using empirical risk minimization? Or?
So I'll talk about the next lecture. So that's one way, just to put everything in one bag and train the ERM on the union of these diverse domains. But there are some other techniques that will cover them in the next lecture.
Okay, thank you.
Sure. Okay, and yes, for the first two problems, the unsupervised and semi-supervised domain adaptation, we consider only a single source domain. Okay, so let me move on. As I mentioned, today we are going to focus on unsupervised domain adaptation problem. Okay, so this is the problem setup that we are given M. Okay, so here for simplicity, I'm going to assume the number of samples coming from source and target, they're the same, just for simplicity. So MS and MT is going to be the same as M. So we are given M labeled samples from source distribution Q, X, Y. So these are the samples that I have. I represent them with X, S, Y, S. And I have, again, M unlabeled samples from target, which is PXY. Okay, unlabeled, so I can't have Y, right? So it's just going to be PX. And here my data would be XI target 1 to M. Again, we are assuming we have the same number of samples just for simplicity in write-ups, but you can extend everything to the general case as well. Okay. So we are also going to pick a function class, let's say a class parameterized by a neural network. That's our hypothesis class, H. Class. So my goal is to pick a function from my hypothesis class such that my target error is small. So if I measure the target error, which is the expectation of, let's say, loss of this function, over what? Over samples coming from PXY. So this is the target distribution. So this is my target error. So I really don't care about the source error at the end of the day. So what I care is that if I evaluate this function H that I pick on my target samples, in the test time, so I have labeled target samples. So I have PXY. So I want to have a small error. Okay. So this problem in general is ill-defined. As I mentioned, you can have, your source samples can be completely different than your target samples, or labelings can be completely different. Maybe, let's say you are given, let's say, cat images in your source with like white background, and then you're given cat images in your target with maybe natural background. Maybe the target labeling is not about the cat itself. Maybe the target labeling is about the background, right? So then your labeling is going to be different. So however you're learning a labeling function from the source samples to identify cats versus dogs, and you go to your target, you say, oh, like my labeling is actually completely different. So whatever I learned already was not, was not any helpful for me. It is in fact, giving me very incorrect labels. So in other words, we need to have some assumptions in order to have a well-defined problem. So what are the practical assumptions? I'm just going to call them practical assumptions because I haven't talked anything about the theory of this problem so far. So what are the practical assumptions? So one assumption, the first assumption is about the type of labelings you can have for different images. So that's called covariate shift assumption. So we say two distributions, P and Q, they satisfy the covariate shift assumption if the conditional label distribution doesn't change between source and target distributions. So what does it mean? It means if you, for any sample, for any image that you have, let's say X is in X, and let's say we consider binary classification. Let's say your Y can be 0 and 1. If I look at the probability of a label given an image X, that is the same as the probability under Q for that label given X. In other words, if you are given a cat, let's say your image is a cat, so you don't label it differently under source and target distribution. Both of them, they produce the same true probabilistic labels for that particular image. So you don't label it with a cat in source, and in the target you look at maybe some other elements on the image and then label it very differently. So that's a very sensible assumption, to have at least the labelings are consistent between your source and target distributions. But is this enough? In practice, we need some other assumptions. So another assumption that we have in practice is basically similarity of source and target distributions. I would say marginal distributions. So if you look at the marginal distribution of your source, which is QX, and the marginal distribution of your target, PX, there should be a relationship between them, right? So if they are completely different, then you won't be able to learn anything meaningful from your source for your target domain. So that's the second assumption. And the third assumption is that Okay, so what is the ideal case? The ideal case, if I had a genie, what would I ask that genie? I would say, okay, give me labels for my target domain as well. So if I don't, but if I had labeled target samples in training, the joint error should be small. Right, so what do I mean by the joint error? So if you are minimizing, if you put, basically you have labeled the samples from your source, you have M samples. You are minimizing the loss for those samples. But now let's say you have labeled target samples. You don't in practice, but let's say you have, then you put them together in one joint big ERM, and you hope that this error to be small. In other words, there is a function H star, let's say, that can map your X's to Y's no matter what the distribution of X's are. Right? So if the distribution of X comes from Q or P, it can reliably map them from X to Y. So that's the underlying assumption that we have here. So there are some questions. Gautam is asking, based on 1 and 2, wouldn't the joint distributions be the same? Good question. So assumption 1 says that the conditional distributions should be the same. But here I'm like hand wavy, right? So I'm not saying they are not equal, right? So if they were equal, if the marginals were equal, conditionals were equal, the joint would be the same. They are not equal, but they are related. So I haven't even defined what I mean by related, but intuitively we mean that they should have some sort of relationship in order to be able to learn something useful from source to the target. Okay, it should be MS and MT in the joint error. You are right. I'm just, for simplicity, I'm just using M for the whole thing. Where did I write? Did I write something? Yeah, so I'm going to basically use M for the source number of samples and the target, the number of target samples, because I don't want to carry these MS and MT in my notation. This is just for simplicity. Everything you can you can extend all of these arguments to the general case. Also, I'm going to assume we are in a binary classification for now. Just for simplicity, it really doesn't matter. So my Y is going to be either 0 or 1. Okay, Mazda, do you want to unmute yourself and ask your question?
Sure, yeah. So my question is that if we assume the conditional probabilities to be the same, it's kind of similar to assuming, the probability of a given class, of a class given the X is the same for our source and our target, then why are we not just using?
Probability of given X, the probabilities of Y's are the same, not the other way around.
Right, given X, the probabilities of the Y. So is that not related to like a classic Bayes classification rule where we seek to choose the Y such that its probability is maximized given X? And if these probabilities are the same, then isn't the classification trivial to just use the same classification that we used for training?
No. So the reason is that the marginals are different, right? So having the conditional probabilities to be same, it means that there is like this, let's say, these are probabilities, they are like spikes, right? So let's say you have a deterministic mapping from X to Y. it means that you have this really ground truth labeling that can work for both source and target samples coming from either Q or P distributions. But the fact is that we don't have the labeled target samples during the training. So I cannot have a joint training in order to learn that universal mapping, for the source and target domains. The issue here is that the marginal distributions can be different. Now, if your marginal distributions are different, then if you're learning a function mapping from X to Y using the marginal distribution of X and the conditional distribution of marginal distribution of your source and the conditional distribution, of course, the conditional distributions match. But since the marginal distributions are different, then the function that you are going to select may not be good for the target distribution. So you cannot ignore the marginal distribution on X because those are your training samples, right? So the reason that we, in the regular training, we didn't, worry about it because the assumption was that my source and target comes from the same distributions, but here your marginal distributions are different.
I understand. Thank you.
Sure. Any other questions? Okay, so if not, let me move on. So first, I'm going to cover some theoretical foundations of domain adaptation from the seminal work by Ben David and co-authors. We posted the paper on the course web page. So again, we are going to consider binary classification, as I mentioned, for simplicity. Classification y belongs to 0 or 1. So now I'm going to make assumption 2 more concrete. Right? So here I'm saying they're related, but I haven't even talked about how they're related. So visiting assumption 2, we want to see how we can define a relationship between QX and PX. Okay, so let's first look at one example before going into the mathematics of it. So let's say I have 2 domains. I have a source domain. Let's say I have these labels, pluses, and these are samples with minus labels. This is my source domain, source samples QXY. And let's say I have my target samples to look like something like this. You have some domain shifts, right? So your samples are not happening on top of each other. So there is a shift between your source and your target. So these are target samples coming from your distribution PXY. Okay, so what do I see in training? Right, so when I'm looking at the marginal distributions, PX and QX, I don't see the labels. Right, so what I see, they are just some points from source here and some points from source here. I don't see the labels, right? So these are my QX samples. And same for the target. These are my PX samples, right? So that's what I have in my assumption 2, that the marginals should be related to each other. Okay, so are these marginals the same or different? Okay, obviously they are different because, you know, they have densities in different parts of the space. So how can I measure how similar they are? Yeah, of course I can use some distributional distances like total variations, but they are very expensive to compute in general. But at the end of the day, what I also care is the similarity or differences of these marginals from the lens of my hypothesis class. Right? So maybe two distributions are, you know, different, but from the point of view of my hypothesis class, they're roughly speaking the same. So one way to think about this problem is to pick a hypothesis to see if that hypothesis would you know, have different perspective for my source and target samples. Let's say I pick this hypothesis. So that's my, it doesn't have to be actually linear, just to be clear. Let's say this is my hypothesis, H. And my hypothesis maps the points on the right-hand side to 1 and on the left-hand side to 0. So that's my one member of my hypothesis class. Okay, now maybe I can just, you know, focus on just one side of my hypothesis function. Let's say look at this part of the space. And I look at the difference of the fraction of my source and target samples that happen to be in this side of this space. Right, so I look at the probability of, let's say, hx is 1 if x is coming from my source, and I look at the probability of hx to be equal to 1 if x comes from the target. Okay, so this is source, this is target. Okay, so in this example, what is the probability of hx to be 1 if x is coming from my source sample? Roughly speaking. No, it's not 1. So what is this term? This term is the fraction of source samples that happen to be on the right side of my hypothesis class. Yes, 0.5, right? So roughly speaking, this is half, because half of my samples in the source are in the right side of this hypothesis class. H of x is 1 for them. Okay. So what about this quantity for the target samples? What is the probability of h of x to be 1 if x comes from my target distribution? Basically, fraction of my target samples. Yes, exactly. So it is half. So in other words, at least for this hypothesis, from the point of view of this you know, hypothesis function, from this function h, source and targets are, you know, quite the same. So can I come up with another function in my hypothesis class that from the perspective of that function, source and target can be very different? Horizontal, yes, exactly, right? So let's look at another function. Okay, so I need more color. So that's a good thing about, you know, having an iPad, so you have more colors. Let's say I pick this function. So let's say that's my h2 of x. And let's say this part h2 of x is 1. And this part h2 of x is 0. Okay, so let's do the same practice for h2 of x. What is the probability of h of 2 of x to be 1 if x comes from the source? Right, so what is that probability? H2 of x is 1, so I'm just going to look into this part of my space. What is the fraction of source samples happen to be in that part of the space? Yes. So it is basically almost all of my samples, right? So that probability is close to 1. All right, so what is the probability that H2 of x is 1 when x comes from my target? So how many, what's the fraction of, what is the fraction of my target samples on top of this hypothesis class, hypothesis function? 0, right? Because all of my target samples, they are below that function. So this is 0. So, and you see, wow, like this is different, right? So this is like the maximum difference that you can get from 0 to 1, because these probabilities are, you know, from 0 to 1, right? So from this point of view, from the point of view of this function, yeah, the source and targets are different. So based on this intuition, we define the following distance between the marginal distributions of source and target. So it is called H-divergence. So it basically looks at the two quantities, probability of h of x to be 1 when x comes from your source, and subtracted with probability of h of x to be 1 when x comes from the target. Look at the absolute value of this. But for which h? So I'm going to look at the worst h, because I want to find a function that can distinguish between source and target. So I'm going to look at supremum over h. And for some mathematical convenience, we multiply it by 2. Really doesn't matter. So this is defined as, so let me write it here. So this is defined as H divergence between my source marginal and my target marginal. Okay. Is this clear? Right, so it may sound a little bit scary just looking at this formula, but you see it is like super, super simple. It is really nothing. You know, you just look at the fraction of samples, at the difference of the fraction of samples on one side of your hypothesis, and pick the worst hypothesis to distinguish between your source and target. Okay, so there's a question. Do we do it for only one class, for multi-class case? So for multi-class case, it is a little bit, you know, you have a little bit of a variation. So one definition is based on 1 versus all. So you do 1 versus the other k-1 classes. I'll talk about it at the end, so don't worry about it. So if the question is H trained? So yeah, I'm basically trying to, I should pick the worst H, right? So now you're thinking algorithmically about this. So how can I compute this? So I'll talk about that in a minute. Based on what criteria does H give the label? So I haven't even talked about labels here. You know, I'm just trying to find a distance between the marginal distributions of my source and target. So it has, you know, so far it has nothing to do with the labels. Okay, so let me move on. I'm running way behind than what I expected. So probably next lecture, we are going to also focus on the domain adaptation, and the lecture after we'll talk about domain generalization. But that's fine. I think the definitions, these definitions are very important to have an intuition for. So let me actually give another example to see we build some intuition about this problem. Okay, let's say I have, again, my source was red. I have some source samples. And I have, my target was pink. I have some target samples. So again, red is source, QXY, pink is target, EXY. Okay, so what do you guys think? Are these two distributions the same or different? Okay, so I see that there's an answer different. Okay, so let's measure the H divergence between their marginals. So first I need to look at their marginals. Okay, so what do I get? So I get some red points here, I get some red points here, and then I'll get some pink points here, and then I'll get some pink points here. Okay, so what would be, what is the H divergence between these two marginals? So this is PX, that's the marginal, and QX. Now, from the marginal point of view, are they the same or different? From the marginal point of view, they look like the same, right? For whatever function you pick, let's say you pick this function, H, the fraction of samples on that side of the classification function is going to be roughly the same. Even if you pick other functions, then it's going to be the same. So in other words, the H divergence between these two distributions are going to be very small. Then what is going on here? But I know like it's gonna be hard to learn a function intuitively, one function mapping from x's to y's for both source and target. What is going on here? So maybe this distance is not good, or what else? Rename labels. How I don't have labels in my training, right? So how do I know I should rename the labels? Okay, good. So let's think about other assumptions that we had, right? So the first assumption was that the labeling, the conditional distributions should be the same, right? So if you think about them as densities, then you can say, okay, if this part of my space, X, are assigned to different labels using Q versus P. But let's say, I carefully design these distributions to satisfy, the covariate shift assumption. But even in that case, think about assumption 3. The joint error should be small, right? So the joint training error, whatever your classification, let's say you have a training and this is your H star, the best classification that you have, maps them to here to the label 1, you are going to have a lot of errors because the labels are somehow intertwined. So this guy, the joint, where is it? This guy is going to be really, really large, close to half, for this example, right? So now we kind of get a feeling, right? So this distance between marginals are important, but it is not like the end of the game, right? So you can have distributions with the H divergences between them to be small, but have bad performance in terms of the domain adaptation. Okay, let's see. All right, so let me move on. So the divergence that we define, the H divergence that we define, one main property of it is that it can be easily estimated. So let me first have this lemma and then say how it will be, how we can estimate it in practice. So DH, the H divergence that we have can be estimated by, let's say, M samples from source and target domains. Let's say the VC dimension of my hypothesis class is D. This is VC dimension. So I already talked about the marker complexity. VC dimension is basically very related to that. It is the largest set of points that a hypothesis class can shatter, and it shows like the complexity of the hypothesis class. If that's the case with probability 1 minus delta, if I have M samples from my distributions, I have a bound on the true H divergence between them by H divergence between their empirical versions plus some number that depends on VC dimension, the number of samples, and M, which is the number of samples that we have. So if M is large enough, so this term goes to 0, and the empirical estimate and the true H divergence between Px and Py can be sufficiently small, the difference between them. Okay, now what about the method? What is the method that we can estimate H divergence? So from the intuition that we have, actually we can estimate H divergence by just solving that supremum over H, which is like finding a classifier that can classify source versus target domain. So in other words, H divergence can be computed by finding a classifier to separate source from target. Right, so if you have some source samples, let's label them by 1, right? So these are my source samples. I don't have the true labeling for them, but I know they come either from source or target, right? So I'll label them by 1. And for my target samples, I'll label them by 0. And then I fit a classifier to classify between source and target and see how that classifier performs. Right, so basically this is the procedure: label all source samples I plus 1, label or target samples by 0, and then train a classifier to minimize the error. So what is the error? What is the classification error in this case? Classification error is I want to pick the best classification hypothesis in my hypothesis class, minimizing the classification error. So for source, I'll have one unit of error when my function outputs a label 0, because I know my sources are labeled 1, right? So if I have a label 0, so this will be error for my source. For my target, I'll have one unit of error if my function outputs a 1, because I know the target are labeled by 0. So that will be the classification error that I have. So if my classification error is large, let's say loss of my classification, if this is large, what can I say about the divergence between H-divergence between source and target? If I'm able to basically classify them with this function, so let's say if this classification is 1, right? So let's look at this example. All right, so here I have a function that can classify with an accuracy of 100%. So my classification error is 0. Then it means my divergence is very large, right? So they're very far from each other that I'm able to classify without any error. So if my classification loss is small, it means my divergence is large, and vice versa. Classification is small, it means I have a function that can separate both of them, so it means the divergence is going to be large. But interestingly, so there is a clear connection between the classification loss and the H divergence. So in fact, if I just look at half of my H divergence, half because in the definition we had a 2. So this is in fact equal to 1 minus my classification loss. Right, so in other words, in order to estimate this H divergence, what I need is to just train a classifier, look at the error, and 1 minus of that would be half of the H divergence between Q and X.